Hello, grade 10 students, and welcome back. Today, we will cover lesson 5.3 Forces in Two Dimensions, part 3. We will also walk through the corresponding applications and homework questions. Let's get started. Decomposing a force. Any given force or any other vector quantity can be decomposed, broken down, or projected into two perpendicular components in a two-dimensional coordinate system. The horizontal component, or we can say this is the x component, and the vertical component, or the y component. The rule for decomposition is as follows. For a force making an angle theta with the horizontal axis or the vertical axis, we will see the two cases later, we will apply f cosine theta and f sine theta to complete the decomposition. To visualize this, we project the force vector along the horizontal and vertical axis, forming rectangular shape where the diagonal is represented by F. So whenever we have force, we just take the tip of this force, the head, and we project it along x-axis, we project it along y-axis, and as a result, we will get a rectangular shape. The diagonal of this rectangular shape will represent what? The force. And the side, the horizontal side, represent the f of x or f of h. And the vertical side of this rectangular shape represent the f of y or the f of v. Now, how we can determine the sign for each component? The sign of each component depends on the quadrant in which the force lies. Now, for example, here the F is in the first quadrant. So we can see that both f of h and f of v are positive, rightward and upward. Now, what if the force is in the second quadrant? Then we can see that the fv is positive and the fh is positive, since fv is upward and fh is leftward. In the third quadrant, both fh and fv are negative because leftward and downward. And finally, in the fourth quadrant, fh is positive, fv is negative because fh is rightward, fv is downward. Now, the first remark here, as the magnitude of f increases, represented by the vector here, the length of the vector, we will see that also the FH and FV will be affected. So they will be changed. Now here, we can see that the length of the F is increased, as well as FH and FV, or FX and FY. As the F increases, also FH and FV will increase. Remark 2, as the direction of force represented by the angle changes, the magnitude of each component also changes. So as theta increases, which means bringing F closer to the y-axis, then also FV will increase. So let me get back to the previous image or previous sketch. We can see that the length FV is with this amount when the F has this angle. Now, if we make the F closer to the y-axis, the FV increased, the FH decreases. Now, if we increase it again, the F closer now to the y-axis, the FV longer, the FH shorter, and until F is perfectly aligned with the y-axis, like this one, it's totally aligned with the y-axis. Then here, the fx is 0 or the fh is 0 and only component is fy or fv. Now, on the other hand side, if f is perfectly aligned with the x-axis, which means f is horizontal, then there is no any y component for this force, and the only component here is the fx or fh, decomposing a force. Now we can notice two cases for the measured angle. The first case is the measured angle with respect to the x-axis, such that the measured angle is in between the force and the x-axis. Now, if this is the case, then we should write the component as the following. Fh is equal F cosine theta, so the cosine should be applied for the Fh, and Fv is equal F sine theta. Now, this type of angle is known as the horizontal angle, or we can say this is the x angle. And I mean by x angle or horizontal angle, the angle that is measured with respect to the x-axis or the horizontal axis. So always we apply the f cosine for the horizontal component or the f of x. And f of v is just the y component fy. Now, in the second case, the measurement is different here for the angle. We can see here that the measured angle is between the force and the y-axis. Such like this angle is known as vertical angle, or the y angle. And I mean by the y angle, the vertical angle, the angle that has been measured between the force and the y-axis. Now, if this is the case, then we should apply the f cosine for the y component because the measured angle is with respect to y. And directly we can say that the fx should take the f sine theta. So let me recall that if the angle is horizontal angle or x angle, then the cosine should be applied for the horizontal component. If the angle is vertical angle or y angle, then the cosine should be applied for the y component. So it's about the cosine, f cosine, where we should apply it. And this is can be done by related it to the measured angle. If the angle is x, then the cosine for the x component. If the angle is with respect to y, then the cosine should be applied for the y component. Now, finally, after we found the magnitude for each component, we just represent it using the matrix notation. In the matrix notation, we draw bracket, we write the x component here or the horizontal component here, and we write the y component in the second entry. So we have two entries. This is not an operation. We are not trying to divide this over this. We just trying to show our outcome using this way of representation. Now, example one, determine the components of F. So we have force F and the measured angle is 30 degree. Now we know that the components are FH and FV, rightward, upward. First, we need to determine the type of the angle. The type of the angle here in this case is with respect to the horizontal, as we can see here, the angle between the force and the x-axis. So this is with respect to the horizontal or x type. Now we're gonna apply the cosine for the FH. Now the f is given by 12, the cosine is, the angle is 30, so the final answer should be 6 radical 3 Newton. Now, since we have applied the cosine for the horizontal component, we're going to apply the sine for the vertical component. Again, f sine theta, 12 sine 30, and the magnitude of this force is 6. So, in other words, this is 6 radical 3 Newton, and this is 6 Newton. Now, finally, we need to show our outcome by using the matrix representation such that the first entry should be for the FH, the second entry should be for the FV. Don't forget to include the signs for each component. Now, since FH is rightward and FV is upward, so both are positive, this is why in the matrix notation we have them in positive signs. Next example. Again, we need to determine the component of F. Now, as we can see here, F is in the fourth quadrant, which means the y component is negative, the x component is positive. The measured angle here is with respect to the x, or this is the x type angle, which means the cosine should be applied for the horizontal component. So f cosine theta, where f is 30, as well as the angle, and we will get 15 radical 3 Newton. This is the horizontal component. Since we have applied the cosine for the horizontal component, now it's time to apply the sine for the vertical component. However, here the vertical component is pointed downward, which means we need to add the minus sign, as we can see here. Now f is 30 sine 30, and the answer is minus 15 Newton. Again, we need to represent the outcome using the matrix notation. For the first entry, we have the x component or the horizontal component, and it is equal to 15 radical 3. For the second entry, we have the y component or the vertical component, and it's equal to minus 15 Newton. Now here in this case, we can notice that this angle is not x type, this is y type because it's measured between the f and the y axis. Now the corresponding components are fh and fv, where fh, as we can see, is leftward, fv is upward. Now theta is with respect to the vertical, which means the cosine now should be applied for the vertical, as we can see here. And for the horizontal, we have applied the sine. Now minus f sine theta, because fh is to the negative direction, minus 45 is the magnitude, 60 is the angle, and we got 22.5 radical 3 Newton is the magnitude, the direction of the horizontal component. Now for the vertical component, we apply the same thing. And finally, we represent the data, the outcome using the matrix notation. Now let's solve these questions together. We need to decompose the vector f or the force f into two components, and then we should show our outcome using the matrix notation. Now the type of the angle here is with respect to the y, that is with respect to the y, because the measured angle is between the force and the y-axis. This is the y-axis. So let me write here f, and we decompose it into f h and fv. Now this is the third quadrant. Everything is negative here, so negative, negative. Now since this is y type, the f cosine should be applied for the vertical component. And directly we write f sine theta for the horizontal component. Now f is given by 100 sine the angle, and the angle is given by 25 degree. And here we have the minus sign, minus 100 cosine 25 degree. Now the values are minus 42.2 Newton and minus 90.6 Newton. The matrix notation is, for this given force, minus 42.2 minus 90.6 Newton. So again, we need to decompose this force into two components, Fh and Fv. Remember that Fh, it can be written as Fx, and Fv can be written as F1. So the horizontal is the same as the x-axis, the vertical is the same as the y-axis. Now the theta measured here is with respect to the x-axis, so this is theta x, which means we're going to apply the cosine for the x component. So f of x is equal f cosine theta, and f of y is equal f sine theta. Now we can see here that this force is in the first quadrant, which means fx and fy both are positive. Now the magnitude of f is 400 multiplied by the cosine of 15, and the answer is 38.6.3 Newton. For this one is 400 sine 15 degree, and the answer is 103.5 Newton. Now finally, we use the matrix notation to represent the outcome. 386.3, 103.5 Newton, where the first entry represents the Fx or Fh, and the second entry represents the Fy or Fv. Now here the angle is with respect to the x-axis again, so this is theta x. So the f should be written as f equal f cosine theta, and here f, let's call it fh, and this is fv, f sine theta. Now for the f cosine theta, or the horizontal component, the force is in the fourth quadrant. In the fourth quadrant, the f of x or f of h is positive, the f of v is negative. So let me add here negative sign. The f is 20 multiplied by cosine 45 degree, 20 or minus 20 multiplied by sine 45 degree. So the answers are 10 radical 2 Newton minus 10 radical 2 Newton. Final step, the matrix notation. 10 radical 2 is for the x component, minus 10 radical 2 for the y components. And for each force, we need to show or represent them using the matrix notation, which means we need to find the horizontal component, vertical component for each one of them. So let's start with F1. Now for F1, the angle, measured angle here is the x type, so x angle with respect to the x-axis. What I meant by x dash theta is the measured angle is with respect to the x, because as we can see here, this angle is between the force and the x-axis. So this is x type, which means the cosine, f cosine should belong to the x component or the horizontal component. Since f1 in the first quadrant, the f of h is positive as well as f of v. Now f of h is positive and it's written as f cosine theta. F of v also is positive, this is f sine theta. Now this is 8 cosine 39 degree 8 sine 39 degree. So the answer is 6.2 Newton and 5.03 Newton. Now finally, we should represent F1 using matrix notation. The first entry for the horizontal component, the second entry is for the vertical component. Now this was F1. Now for F2, we have F2H and F2V. Now as we can see here, F2 in the second quadrant, which means F2X or the horizontal components is negative, F2Y or V is positive. Now F2H is negative F2. Now this is X type or Y type? As we can see here, the measured angle is with respect to the Y axis, between the force and the Y axis. So this is Y type, which means the cosine should be applied for the vertical component. So let's write here sine theta and here F2 cosine theta. Now minus F2 is given by 10, the sine of the angle, 27 degree. Here we have 10 cosine 27 degree. Minus 4.5 Newton and 8.9 Newton. So the F matrix notation, this is F2, is written as 4.5 and 8.9 Newton. Now, here in this question, no need to decompose the forces because they already presented in perfectly in one of the axes, such as F1 is perfectly aligned with the x-axis, F2 is perfectly aligned with the y-axis. So F1 is the same of FH, which is equal 40 Newton. What about the FV? The FV is 0 here. And for the F2, it's completely aligned with the y-axis. So this is the FV, which is equal 20 Newton. But since it's directed downward, we will need to add the minus sign. And for the FH, it will be 0. Now let's use the matrix notation to represent each force. The first entry always for the horizontal component. The vertical component is 0 here. For F2, the horizontal component is 0, no horizontal component anymore. We have only vertical component, which is equal to minus 20 Newton. Now express each of the following forces in matrix notation. Now in order to do that, we're gonna work on each force independently. So let's start with F1. So I will start here with F1. For F1, the measured angle here is with respect to the x-axis. So this is theta with respect to x, which means the cosine should be belong to the x component or the horizontal component. So let me write F1H and F1V. And we can see here the forces in the first quadrant. In the first quadrant, everything is positive. So F1 cosine the angle, F1 sine the angle. Now F1 is given by 10, cosine the angle is 30, and 10 sine 30. The values are 5 radical 3 Newton, and here we have 5 Newton. So F1 in a matrix notation is 5 radical 3 and 5 Newton. Now let's jump into F2. As we can see here for F2, the measured angle is again with respect to the x-axis. which means we're gonna apply the cosine for the x component. So theta here is with respect to the x-axis. F2x and F2, let me write it as F2h, just for the consistency, because I used here h, so I will complete the using the same index for the other forces. So F2v. Now this is second quadrant. In the second quadrant, the forces are up for the vertical, left for the horizontal. So positive for the only vertical and negative for the horizontal. Again, the cosine should be applied on the horizontal component and F sine for the vertical component. Now this is minus 5 cosine 65 degree. This is 5 sine 65 degree. The answers are minus 2.11 Newton, 4.53 Newton. So the matrix notation of F2 is written as minus 2.11, 4.53 Newton. Finally, we'll decompose now F3. First, we need to determine the type of the angle. As we can see here, the angle is with respect to the y-axis. So this is theta y, which means we're going to apply the cosine for the y component or the vertical component. So let me write here F3 theta is with respect to the y on the vertical axis. So F3 should be decomposed into F3x and F3y. Now, this is the third quadrant. Everything is negative here in the third quadrant. So let me write F3 sine theta because the angle is from the type of V, vertical or Y, then the cosine should be applied for the vertical component or the Y component. Again, let me use the same notation that I have used in earlier questions. So let me write here horizontal and vertical. Uh, and let me recall that the FH is the same of FX, so you can use them exchangeably here in this question, as well as for FV. You can write FY. Now, minus F3 is given by 8. Sine the angle is given by 12. And here we have minus 8. This time we're going to apply the cosine because the type of the angle is with respect to the vertical. Now the values are minus 1.66 Newton, minus 7.82 Newton. So the F3, now the matrix notation is written as minus 1.66 minus 7.82 Newton. That's it for today. Thank you for watching and see you in a new video soon.